morning, students. In the yesterday's class, we were seeing electric lines of forces because of the network problem. We stopped in the middle. Mm. So we'll continue the electric lines of forces. So as I mentioned yesterday, this electric field is invisible. Mm. So only through the charges, through some devices, we can detect the electric field. We cannot visualize them. So Michael Faraday introduced the concept of electric lines of forces. Even you are seeing magnetic lines of forces also. I think you might have learned in your lower class magnetic lines of forces. Electric lines of forces, magnetic lines of forces is an attempt to visualize the unseen electric field. How may be the electric field between the charges? Where it may be strong? What is the direction of the electric field? So these things you can visualize through these electric lines of forces. It is visualization of the unseen hmm, electric field. Okay, so how it is drawn. If you have a positive charge here, around that electric field will be there, but we want to visualize it where the electric field is strong. What is the direction of it? Where it is weak, I want to know the electric field due to this positive charge. To what extent it will extend. So these things you want to know. Okay. So for that, what we have to do? A small positive charge, a very small positive charge, whose effect should not be there on this source positive charge, whose electric lines of forces we want to draw. Effect of this positive, small positive charge that we have chosen should not be there on this. If it is there, it should be negligible. Okay. So when we place it very close, when we place this charge very close to the positive charge whose electric field is to be found, electric lines of forces is to be drawn. If you leave it here, what path? So this positive charge, what path this positive charge takes? So what it will be? This will be repaired. So this is the line joining the two charges. Line joining the two charges. Positive charge and positive charge. So this will be repaired. It will be repaired. So it will move here. This positive charge will come here after repulsion, after some fraction of time. Once again, the repulsion will be there. It will be moved here. It will be moved here. So it comes here. So of course the force of repulsion is decreasing now, but definitely it will be repaired. So in the sense, this positive charge, small positive charge, it will travel in this path. It will travel to what extent? hmm, the electric field is there. Of course, as it is moving away, it is a decreasing. Electric field is continuously decreasing. Electric field is continuously decreasing. The same way is like this. Here, if I keep that positive charge, if I keep this positive charge here, so it starts to move in this path. If you keep this positive charge here, hmm, it will start to move in this path. It will move in this path. So if we keep it here, this will be move in this path. So this will be the uh, these are the electric lines of forces. Practically, uh, if it is theoretically speaking, so these lines of forces will extend up to infinity, because theoretically speaking, under ideal condition, electric field extends up to infinity. Okay, but practically around this charge, to some extent we can draw these electric field will be there, and we can draw these electric lines of forces. In fact, what you can see here, it is a geometrical representation of the path followed by the positive charge. We are drawing it. We are drawing it. How the positive charge is moving. How a small positive charge, a negligible magnitude positive charge, how it is moving, we are drawing it. We are drawing it. The geometrical representation of the path followed by a very small positive charge, we say it as electric lines of force. Okay, if it is negative charge, if it is negative charge, isolated negative charge, no other charges are present close to it. Hmm. So if we keep this is very small unit positive charge, very small positive charge, always use to draw the lines of forces, we use the positive charge. Okay, so what path it will travel? Hmm? So it will move in this direction, because there will be force of attraction. It is a positive charge and this is a negative charge. So if I keep a positive charge here, somewhere here, so what it will be? This will be attracted. So if we keep here, it will be attracted. If we keep it here, the electric field is inside. Electric field is inside here. So this arrow, because it will be attracted. So this starts to this positive charge. This positive charge start to move towards it. If this is the positive charge, it starts to move towards it. In which path the positive charge travels, so that will be our electric line of force. So for an isolated positive charge, For an isolated positive charge, how will be the electric lines of forces? So electric lines of forces for an isolated positive charge. One of the important question for 1 mark or 2 mark they will ask. Draw the electric lines of forces for an isolated hmm, positive charge. For an isolated positive charge. Anywhere you can draw this arrow. In the same way, for negative charges. So this will be the geometrical representation of electric lines of force for an negative charge. This is for positive charge. How a very small positive charge, how it moves, what path it traces, what path it will travel. So that path traveled by that path traveled by that positive charge, we are representing it like this. So this itself will be our electric lines of forces. So these are isolated positive and negative charges. If we have one positive charge and other negative charge, one is positive, other is negative. So what it will be? I'll keep that very small positive charge here. So what it will be? This will be repelled. This will repel this, whereas this will attract it. Hmm, It will attract it. So it starts to move in this way. It will come at this point. It will repel and this will be attracted. It is in this way. When it comes to this point, so this will be repelled, this will be attracted. So this path it will take. So it will take. So one electric line of force will be from positive to negative. Next, if I leave a positive charge here, if I keep a positive charge here, so what it will be? So this positive charge is, it is repelling it. This positive charge is repelling it in this way. Whereas this negative charge, along the line joining the two charges, the force acts along the line joining the two charges. So what it will be? So this will attract it in this way. In which direction it will move? Huh? Vector sum of these two forces. In the sense, you are completing the parallelogram. You are completing the parallelogram. So this charge will move in this direction. It will neither go like this nor it will go like this. It moves in between like this. So it will come somewhere here. This positive charge will come somewhere here. So now this will be positive and positive. This will be repaired like this. This will be repaired like this. Whereas this is attracted like this. So vector sum of these two. So in this way, if we draw, how will be the electric line of force will be somewhat like this. Electric line of force will be in this way. Of course, it will be from positive to negative. The direction is from positive to negative. So it is starting from positive, ending here also. It should start from positive. It should start from positive. It should. Whereas it is ending. It is ending like this. So they may ask you for a positive and a negative charge, how will be the electric lines of forces? Hmm? Even we say it as a dipole. I'll come to that later. A positive equal positive and a negative charge. We say it as a dipole. Electric, draw the electric lines of force for a dipole. They'll ask. It will be like this. If both are positive charges, if both are positive charges, how it will be? So here is our positive charge. If I keep here positive charge, so what this does? So this will be in this way, whereas this also will repel in the sense it will move it in this way. Of course, it will be smaller in length compared to this if it is longer, because the force will be more here, whereas force will be less here. Vectorially, if we represent, force is less here, force is more here. So vector sum of these two. it will move, it will take you in this way. So when it comes here, what it will be? So this will be repaired like this. This is repaired like this, whereas this will be repaired like this. Hmm? Vector sum of these two will be in this way. See how the charge is moving. The charge is moving like this. Hmm? So if you draw it, how this will be? It will move in this way. So this will be if both are positive charges. Hmm? How will be the electric field? It will, its electric field is acting like this, its electric field is acting in this way. So that is represented by the electric lines of forces. If both the charges are positive charges, then we represent it in this way. Now saying properties of electric lines of force. Properties of electric lines of force. What properties it has? First property, the electric lines of forces are continuous. Hmm? As I'm saying, I'm drawing a continuous positive, exactly how the positive charge moves. hmm, In the same way, what path it will travel, the same path, in the same way we are drawing the electric lines of forces. So, what it is? Electric lines of forces are continuous. Hmm? They are continuous, smooth curves without any break. They are continuous, smooth curves without any break. Okay. Second, so if positive charges we have, if we have an isolated positive charge, what we have seen? Diverged electric lines of force. Electric lines of forces are diverged, isn't it? So if a negative charge is there, so then electric lines of force in the same way, but they are converged electric lines of force. For an isolated positive charge, the electric lines of forces are diverged. If an isolated negative charge is there, the electric lines of forces are converged in nature. Positive charge diverged, negative charge positive charge diverged, negative charge converged. Next, third point. You can see in the in a dipole, positive, negative dipole, how the electric lines of forces, they are starting at positive charge, ending at negative charge. They are starting at positive charge and ending at negative charge, but cannot form a closed loop. They cannot form a closed loop. Starting from positive charge will end at negative, but never. It will start from negative and close at positive. It will not form a closed loop. It will start at positive, end at start at positive, end at negative, start at positive, end at negative. So it will start at positive charge, end at negative charge, but not form a closed loop. Form a closed loop. It will never form a closed loop. What is? The electric lines of forces are smooth, continuous, never break. It is a smooth, continuous, they never break. Second, if it is isolated positive charge, electric lines of forces are diverged. Isolated negative charge, electric lines of forces are converge. Then third point, it will start at positive, end at negative, but never form a closed loop. The one which is starting from a positive, end at negative, but never it will start from negative and positive, like it will never form a closed loop. So start at positive, end at negative, start at positive, end at negative. Same. Tangent drawn to, if I want to know the electric field at this point, due to these two charges, what is the electric field I want to know? Okay. A tangent drawn at this point to the electric line of forces. If I want to know the field at this point, draw a tangent here. Draw a tangent to the electric line of force. So that will give you the direction of the electric field. It will give you the direction of electric field. Tangent drawn to the electric line of force represent the direction of the electric field. What is tangent drawn to the electric line of force at a point hmm, represent hmm, direction of electric field. So anywhere you draw the tangent to the electric line of force. So that shows the direction of the electric field at that point. Next, no electric lines of forces intersect no electric lines of force intersect. Hmm. So I can see here if any electric lines of force, if they are intersecting at any point, if they are intersecting. So just now I mentioned a tangent drawn to the field, to the electric line of force, represent the direction of the electric field. So what it is? So we are drawing a tangent to this electric line of force. So at this point, the direction of the electric field is in this way. We are drawing a electric line of force in this way. See, so tangent I am drawing here also, tangent I am drawing here also. In a sense, at one point, the direction of the electric field is two. One is like this, another is like this, which will never possible. At a point, electric field, the direction of the electric field should be at only one direction. So if it is like this, at this point, what it represent? At this point, two electric field exist there. It represents it so. It represents the two electric fields are exist at that point, which will never happen. At one point, so whatever may be the number of charges, however may be the number of charges, how many may be the number of charges. So at a point, it gives the sum of all those. Vector sum of electric field is vector sum of all those charges. In the sense, vector sum, however, let it be 10 such electric charges are there. Vector sum of all those will be the electric field at a point. So electric field like this double electric field does not exist. So if it is not possible, means this crossing of the electric line of force is also not possible. Crossing of the electric line of force is also not possible. If they cross like this, so electric field at this point has got two direction. In the sense, at this point, two different electric field exist, which will never possible. We should have at a point, we should have only one electric field, only one direction it should be. So then, so this crossing is never possible. They have to be separate like this. They have to be separate like this. Never two electric lines of forces cross each other. If they cross, two electric field, which is not possible. So therefore, no electric lines of forces intersect each other. No two electric lines of forces intersect each other. So next, if we have a charged conductor, if we have a charged conductor like this, it may be like spherical shape in this way, or it may be, it is like this. So charges always reside on the surface. Charges always reside on the surface. In the sense, if negative charges are present, so these negative charges are, they reside. No charge is present inside. Inside the sphere, if it is a solid sphere, inside the sphere, no charge exists. Because, let us say, if they are present inside, if they are present inside like this, what happens? So this will be repaired by this. So it is moving this way. It will be repaired by this. It will be moved this way. This will be repaired by this. It moves like this. So like this, they gone moving as possible as. To what extent they can move? Till to the surface of that conductor, they can move. They cannot cross that surface. So these charges which may generate at the center of a conductor, solid conductor, which may generate at the center of the solid conductor, but as soon as they generate, they get repaired by one another and starts to move away from one another, and finally they reside on the, finally they reside on the surface. Okay, so these charges, they will reside on the surface. Always in a conductor, charges reside on the surface of the conductor. Okay, so now it will reside here also. It will reside on the surface like this. It will reside on the surface like this. Okay, so now coming to the next property of electric line of force. So electric line of forces are always normal to the surface. These will be, if this is normal to the surface. Okay, electric lines of forces are always normal to the surface of a conductor. Always normal to the surface of a conductor. If they are not normal, what may happen? We'll think in that way. In fact, they will be normal to the surface if they would have not been in normal to the surface. Let us consider the electric line of force is somewhat like this. Electric line of force is somewhat like this. So this, since it is being a vector, we have to resolve this electric field. This electric field we have to resolve. This electric field we have to resolve into two perpendicular components. Okay, of course, a part of the electric field is normal to the surface. What the other part of the electric field is doing? What it does? So of course this is normal. So what this part of the electric field is doing? It will definitely push the charges which are present here. It will definitely push the charges which are present here. If it pushes, the charges are present on the surface. So what this electric field, what this force does, it pushes the charges which are present here. Of course, this will not affect the charges. This component of the force will not affect. So electric field I have resolved into two perpendicular component. Electric field, if this would have been making an angle, some angle, thinking it so, what I have done, if I resolve it in this way, so this component of the electric field, this component of the electric field has to push the charges, and because of the component of the electric field, these electric charges has to move. These electric charges has to move, have to move, which is a contradiction to our electrostatic. In electrostatic, the charges are at rest. They won't move. If only electric field exists, the motion of the charges we cannot see there. Okay, so then the presence of this component of the electric field is not possible. In a sense, so this electric field should not be slanted like this. It has to be like this. In the sense, no other component, no other horizontal component of it will exist. Only it should have vertical one component. The horizontal component should not be there. Horizontal component should not be there. Only we should have only the vertical component. Only the vertical component. If any other component exists, in any other component exists, then so that what that does, it makes the charges on the conductor to move. It makes the charges on the conductor to move. Following my point? So therefore, other component, horizontal component does not exist. Only vertical component exists. In the sense, it should be, this should be always, the electric lines of forces, always they should be perpendicular to the surface of the conductor. They should be perpendicular to the surface of the conductor. Okay, so what it is? Electric lines of forces always normal to the surface of conductor, always normal to the surface of conductor. Electric lines of forces are always normal to the surface of a conductor. Next, electric lines of force electric lines of force do not pass through hmm, do not pass through a conductor. Hmm, it will not pass through a conductor. Why it is? We never get a conductor in this way. Part of it is positive and other part is negative. We never get a charged body like this. Either all the charges should be negative, will be negative, or all the charges should be positive. We never get like this. If it is so, then electric lines of forces will be from positive to negative like this. Inside the conductor I'm talking. Inside the conductor, if all these are positive charges, all these are negative charges, it is like this. So charging will never possible like this. So if you have charged a body, either the whole body should be negative or whole body should be positive. So from negative to negative, so we cannot draw the electric line of force. From positive to positive, we cannot draw the electric lines of forces. In the sense, you cannot draw the electric lines of force here because electric field inside the conductor does not exist. Electric field inside the conductor is zero. Electric field inside the conductor is zero. Where there is no electric field, there will not be any electric lines of force. Where there is no electric field, no electric lines of force. So, electric lines of force does not pass through the conductor because the electric field is not present inside the conductor. Electric lines of forces are not present inside the conductor. Electric field is not present in the sense electric lines of forces will not be there inside the conductor. Okay, so what it will be? Does not pass through electric lines of forces does not pass through a conductor. Next, see, I have drawn the electric line of force like this. For a dipole, how we have drawn? Same. The electric lines of forces at this point, they are very close. Electric lines of forces at this point, they are very close. Electric lines of forces at this point, they are very rare. Or in the sense, the density of the electric lines of forces is more here, the density of the electric lines of forces is less there. More dense here, less dense here. Okay, so what it represents? So dense the electric lines of forces. Dense the electric lines of forces. It represent the strong electric field. The electric field is strong. If the electric lines of forces are rare, if the density is less, if they are rare, then what it represent? If it represents, if they are rare, it represents the electric field is weak at this point. Electric field is weak at this point. Electric field is strong at this point. So the relative closeness of the electric lines of force decides whether the field is strong or weak at a point. So what it is? Relative closeness. Relative closeness decides. Relative closeness decides the strength. We can say it as strength of the field. The relative closeness decides the strength of the field. If they are close, then field strength is more. If they are rare, electric lines of forces are rare, so then it is weak. See, next point. So you can see here electric lines of forces, they are contracting lengthwise. They are contracting, they have the tendency to contract lengthwise. They have the tendency to contract along their length. So that shows the force of attraction. So where there is attraction is there. For example, how it will be if this is this. The electric lines of forces are not like this strong. So because since they try to move towards one another, they try to move towards one another. If they try to move towards one another, so these lines, what they become? They start to contract with one another. So rather than if this is trying to move like this, this is trying to move like this. So what happens here? So it will get contract. It will get a contract. The tendency of lengthwise contraction, the tendency of lengthwise contraction of the electric lines of force denotes the force of attraction, the force of attraction between the two charges. The tendency, otherwise these lines of forces, if they are they don't have any tendency of attraction. These would have been the straight lines. Since they are attracting each other, they are trying to move close to one another. So because of that, what happens? So these get contract along their lengthwise. The tendency of a contraction along their lengthwise denotes the force of attraction between the two charges. Then the tendency of expand laterally, tendency of expand laterally, we try to bring them close, but this tendency to move this side, ಇದು ಈ ಕಡೆ ಹೋಗಕ್ಕೆ ಟ್ರೈ ಮಾಡ್ತಿರುತ್ತೆ, ಇದು ಈ ಕಡೆ ಹೋಗಕ್ಕೆ ಟ್ರೈ ಮಾಡ್ತಾರೆ, ಎಲೆಕ್ಟ್ರಿಕ್ ಲೈನ್ಸ್ ಆಫ್ ಫೋರ್ಸ್. So laterally, the tendency of expand laterally. So lateral pressure on the neighboring lines, they start to put lateral pressure. So if you bring it close, so these starts to apply pressure on one another. These start to apply pressure on another. So this, so lateral pressure on the electric lines of force, lateral pressure on the electric lines of force, so that represent there is force of repulsion between the two charges, force of repulsion between the two charges. So lateral pressure on the electric lines of force, if you bring them close, so these electric lines of force, they start to contract. They laterally, they try to come close to one another. So that shows there is a force of repulsion between these two charges. Okay, so all these are the properties of electric lines of forces, starting from electric lines of forces are continuous, in a sense they won't break. Positive charge has diverged electric lines of forces, negative charge has converged electric lines of forces. Electric lines of forces start at positive charge and end at negative charge. They never form a closed loop. Tangent drawn to the electric line of force at a point represent the direction of the electric field. So no electric lines of forces intersect each other. So electric lines of forces are always normal to the conductor. So electric lines of force does not pass through, it does not pass through the conductor. The relative closeness between the electric lines of force decides the strength of the field. More close the electric lines of force, the stronger the field. So then the lengthwise contraction of the electric lines of force shows there is a force of attraction between the charges. The lateral pressure on the charges represent, lateral pressure on the electric lines of force represent the two charges are repelling each other. So all this about the electric lines of forces, they may the very important questions in the theory, they may ask you to draw the electric lines of forces for an isolated positive charge, isolated negative charge, for a dipole, for a two oppositely, for two like charges. or they may ask you to uh, write any two, any three properties of electric lines of forces. Okay, so we'll stop here. In the tomorrow class, superposition principle of electric field. We have seen electric force. So electric superposition principles of electric field we will see in the tomorrow class. Thank you.